When all four properties of a gas are invited into the same equation, we come up with the ideal gas law. Now, here's what we said. Here's Boyle's law. P times V equal P times V. Charles' law, V over T. Avogadro's law, V over N. These are all relationships that hold true. Pressure and temperature directly related. Volume and moles directly related. Pressure and volume inversely related. All of these are placing the same four variables into one equation. So if you had two sets of equations, you would say, here's the initial and here's the final conditions. And again, this combined gas law puts all the variables into one spot. I don't need to keep memorizing separate equations. PV over NT. One equation gets me everywhere. Now, at standard conditions, and what I mean by that is by saying STP, I'm going to employ Avogadro's law. Let me just write that again. Avogadro says 1 mole of any gas occupies a volume of 22.4 liters at standard conditions, right? At STP, that's the north to the balloon. So why don't we do this? I want to just rearrange this, PV over NT, and I want to solve for R, which is going to be called the ideal gas constant. And what I'll do to solve for R is place in all of those variables that Avogadro told us. So in other words, let's say at standard conditions, STP, let's say we know that's 1 atmosphere, and we know that's 273 Kelvin units. I also know that STP can be measured with 760 as the measurement for millimeters of mercury. I mean, I just know that there's more than one pressure unit. Let's use STP and solve for R, the ideal gas constant. And I'm going to use pressure in 1 atmosphere first. When I have 1 atmosphere of pressure, the volume of my balloon would be 22.4 liters big if I had 1 mole at standard pressure and standard temperature. Do you see how all of these are standard numbers? One mole of any gas occupies 22.4 liters at standard conditions, standard pressure, standard temperature. Let's solve for R. And when I do that, I'm just going to say 1 times 22.4 divided by 1 and 273. Now my screen reads 0.08205. I'm going to round that to 0.821. And keep in mind the unit here would be an atmosphere liter over mole Kelvin. When the pressure is measured in atmosphere, R is a constant, 0.0821. I remember that is August 21st. It helps me remember the number, August 21st, 0821. So when I'm looking at any type of ideal gas law constant, R is determined by the pressure unit you put in. And I said a moment ago, what if instead of atmospheres, what if we used millimeter of mercury? That standard pressure in a millimeter of mercury is 760. And I will plug in all the standard numbers again and solve for R. If I used 760 instead. So 760 times 22.4 divided by 273. And this is a number on my screen, I'll just round a little bit, 62.4. And that comes out to me as a millimeter mercury liter over mole Kelvin, the unit on the R constant. So when I'm looking at the ideal gas equation, here is my combined gas law, PV over NT. PV over NT is our combined gas law, and I set that equal to R, and I solved for R. And we just rearrange this equation to make it a little friendlier, right? We're going to bring the NT up to this side, and that's how we come up with the ideal gas law, just rearranging it. PUV equals NERT, PUV NERT. Now I can remember those variables so easy. PUV NERTs. We're going to practice some PUV NERT problems. PV equal nRT. What does P stand for? Well, that's pressure. What does V stand for? Well, that's volume. What does N stand for? Well, that's the number of moles. What does R stand for? That's the constant. And what does the T stand for? Well, that's temperature. Now let's think this through a little bit. I said that if pressure was measured in an atmosphere, what was the value of R? If pressure is in an atmosphere, R is 0.0821. But if pressure is measured in a millimeter mercury, what is the R value? That was our value that we wrote down, is 62.4. So whatever pressure unit you PUV NERT with, make sure you put in a matching R constant. Match the pressure unit and the R value. The other considerations, when we solved for R, we used liters, didn't we? So when I'm looking at this guy, volume, he must be in a liter unit. Must be, or I didn't solve for R correctly. And the other guy, remember, Kelvin temperatures, always, always for your temperature. The unit you place in for pressure determines the R constant. Volume will be a liter, N stands for moles, and T for Kelvin temperature. PUV equals NERT. Are you ready to try one? I already did this, didn't I, on the previous slide? This is where we wrote down our values for 1 mole of any gas occupying a volume of 22.4 liters. R, if the pressure is in atmospheres, was 0.0821 liter times atmosphere over Kelvin mole. And if R is in a millimeter mercury, it was 62.4 liter mmHg Kelvin mole. Those are constants you need to memorize. Now, you ready to practice one? How many moles of a gas are contained in a typical human breath that takes 5 liters of air at 1 atmosphere and the body temperature of 37 degrees? Now, when I PUV NERT, I like to just get my parentheses ready. In other words, here I know that PV equals nRT. Get your variables ready. PV equals nRT. So that way, when I read this sentence, I now know to just plug into the correct parenthesis. How many moles? Well, that means I'm going to solve for N, right? That's my target variable. The volume must be in a liter, and it is, so that's good, 0.5 liters. The pressure is given to me as 1 atmosphere. And now remember, as soon as you know P, you also know R. Pressure is measured in an atmosphere, so we have to use the appropriate R constant, 0.0821 liter atmosphere over Kelvin mole. Temperature is 310 Kelvin units. PV equal nRT, PUV equal NERT. We're going to solve for the number of moles. To isolate N, you can see PV over RT. So just kind of starting on the side without the variable first. That would be the P times V, does not contain the variable, and then divide by the other side. So over here, you'd have R times T. And just make sure you're putting that in a parenthesis. So your key sequence here would have 1 atmosphere times 0.5 liters divided by the R constant, 0.0821, times 310, close parentheses, and you'll have N. The number of moles is what N stands for. 1 times 0.5 divide by parenthesis 0.0821 times 310, close parenthesis 0.0196. 2 sig figs, so there we have 2 sig figs, 0.020 moles of a gas. We just did our first PUV-NERT problem. How's that feel? PV over RT isolated N. The number of moles is N. Let's try another. If a person exhales 25 grams of carbon dioxide in an hour, what volume does this amount occupy at 1 atmosphere and 37 degrees Celsius? Well, I'm going to get my PUV-NERT parentheses ready. I know that P times V will equal nRT. I'm not hearing a G for grams anywhere. This is not a PUV-GERT problem, is it? It's a PUV-NERT problem. So my 25 grams of carbon dioxide has to be converted into a mole. And to do so, we use the mole map. 25 grams of carbon dioxide needs to be divided by its molar mass, which we did just a minute ago. Carbon is 12, and we found 44 grams as its molar mass. And this then will come out with the number of moles of carbon dioxide. 25 over 44. This gives me 0.568. And since I had 3 sig figs here, I'm going to carry 3 sig figs into the problem. Now that's N, the number of moles in my PUV-NERT problem. So it's not PUV-GERT, it's PUV-NERT. If I'm given a mass, just do a simple mole map problem and get it into the mole. 0.568 moles is the value of N. What volume, so that's going to be my target variable, does this amount occupy at 1 atmosphere? Well, that's a pressure unit. And as soon as I know ATM, I also know R. R has a value, a constant you must remember, as 0.0821. I told you it reminds me of August 21st. If that helps you with a calendar date to help you remember R, it helps me. That's a liter, atmosphere, Kelvin, mole. That's what a derived unit is to make you remember the atmosphere unit matches 0.0821. And then 37 in a Kelvin unit is our 310 temperature. We're looking for volume. So remember, start on the side without the variable first. Simplify the right side. NERT over P. So your key sequence would hit 0.568 times 0.0821 times 310, and then you would divide that by your 1 atmosphere. I have 14.46. How many sig figs? 3. Whoops, the temperature is 2, so we'll give it to 2 sig figs. We'll round it to 14, and that would come out as a liter. How'd you do? You just did another PUV-NERT problem. Just a little smidge different because we had a little mole map side work to do to get an N, the number of moles, when given the grams of carbon dioxide. I'll emphasize, remember, it's not a PUV-GERT, it's a PUV-NERT, where moles are necessary. You try one, come back to me when ready. Pause the video and work this out, see if we got the same answer. Getting my parentheses ready for PUV equals NERT. The volume, how many moles? We're looking for moles. 5 liters is your volume. Pressure 175 atmospheres. So that matches the R constant, 0.0821. Temperature had to go in as 293 Kelvin units. Are you remembering your parentheses when you hit that out? Solving for P times V over RT, 175 times 5 divided by, oh, I hit that wrong already, 175 times 5 over R times T. How about 36.37? We'll need, consider that, so we'll round to 2 sig figs. That's 2 right there, 2 right here. So 2 sig figs is 36 moles. 175 times 5 divided by parentheses 0821 times 293. Yep, 36 moles of oxygen. Well, that makes sense because this is a very, very high pressure. It's going to take a whole lot of particles to get a pressure that high. Did you get a correct answer? I'm sure you did. How about some more? Determine the pressure in atmospheres under each of the following conditions. So if I'm looking for pressure when the volume is 10 liters, 0.45 moles, selecting the matching R constant, and the temperature in a Kelvin unit, 298 Kelvin. We're looking for pressure when I had a 5-liter volume, 10 grams of nitrogen. Well, that had to be a little mole map problem, didn't it? So you had to find the molar mass of nitrogen to get an N. Remember, it's not PUV-GERT, it's PUV-NERT. So 10 grams divided by the molar mass of nitrogen, 28. That was our 0.357. I'll keep all 3 sig figs. Here's your matching R constant, 0821. And the temperature is 20, so that's 293 Kelvin units. So remember, to solve for P, you're going to start on the right side and isolate pressure. nRT over P, nRT over V isolates the pressure. Let's hit these to be sure we get them right. How about 1.10? So 2 sig figs, 1.1. Does that match your page? And here, 0.357 times 0821 times 293 over 5. Here I have 1.7 ATMs. You're doing PUV-NERT work. How's it feel? Pretty good. We've been talking about 52 minutes. So you know what? This is such an easy section. I am going to just push through. Again, if you need a break, please take one, but I'm going to push through this next section because it is simple. It is so easy. We're adding and subtracting. We might as well just do that on this video as well. And this kind of wraps up all of the gas talk, and we'll have had accomplishment then of 2 lessons for gas laws. So the last gas law presents Dalton's law of partial pressure. And in words, we're simply going to say the total pressure of a gas in a mixture is the sum of all the partial pressures of its components. So let's suppose, if you will, I have a container that contains a blue molecule and it's exerting a pressure as 5 atmospheres. And in a separate container of equal size, I have a red molecule that's exerting a pressure of 3 atmospheres. Notice that it's just matching the number of particles. 5 particles gives me 5 atmospheres of pressure. 3 particles gave me 3 atmospheres of pressure independently in separate containers. What if I put them together in the same container, same size, same temperature? What happens to the total pressure? Well, you got it. You just add them together. So if particle A gave me 5 atmospheres, it still is in this one. If particle B gave me 3 atmospheres, it still is. And so the new combined pressure is simply the sum. That's as easy as this gets. You add the partial pressures to find the total pressure in the system. So here I said partial pressure of gas A plus the partial pressure of gas B gave me the total pressure in the system. P sub T is the total pressure. That's what I said, 5 plus 3 gave me 8 atmospheres. However many gases you have, if you have 3 individual gases, you just sum the individual pressures to find the total pressure. I know, right? It's kind of easy. So when we take a look at Dalton's law, it's really just adding and subtracting. Let's model one here. A sample of exhaled air from the lungs contains a mixture of 4 gases. The first of those gases is nitrogen. The partial pressure, notice how I'm writing capital P and then kind of small n2. We're going to read that as the partial pressure of nitrogen is given to me as 563 millimeters of mercury. That's the first of the gases. Then it says oxygen. So the partial pressure of oxygen, notice it's a capital P and then I just put O2 kind of small next to it as partial pressure of oxygen is how we read that, is 118 millimeters of mercury. There's a third gas, carbon dioxide, and it's contributing 30 millimeters of mercury to the total pressure. And we have some water vapor, and it's contributing 50 millimeters of mercury pressure. What is the total pressure? I know. I wish we had a whole test of these, right? We know that the total pressure is equal to the sum of all of the individual contributions from those 4 gases. So I'm knowing that the sum of each pressure will give me the total pressure. So it's as easy as saying 563 plus 118 plus 30 plus 50. I added those together and the total pressure came out to the sum of 761 mmHgs, millimeters of mercury. I know, you're welcome. This one was an easy one. Dalton's law of partial pressure. Each individual gas contributes to the total pressure. To find that, just sum their values. Let's try an example with air. Air is a mixture of 21% oxygen. It is comprised of 78% of nitrogen and 1% argon by volume. What is the partial pressure of each gas at sea level, where the total pressure is 760 mmHgs? So if this is the total pressure The contribution of each gas is just based on its percentage of its contribution. When I write 21%, think of that as being 21 parts out of 100 parts. 21% of 760 gives me the partial pressure of oxygen. 78% of 760 would give me the contribution from the element nitrogen. And 1% of 760 would give me the partial pressure of argon. And those will sum to be 760. So percentages, parts out of 100 parts. 21 over 100, of course, is 0.21 times 760. The partial pressure of oxygen is 159.6 millimeters of mercury. 78 over 100 is 78% times 760. Partial pressure of nitrogen is 592.8. And then 1 over 100 is 1% times 760. That comes out to 7.6 millimeters of mercury. And then just considering rounding to give us sig figs, this could be 160, this could be 593, and this could still be 7.6. So you could consider rounding there and working it into the number of sig figs you'd like to report. Probably 2 for each one, but then we wouldn't have 100% overall. So we're just showing the math here of taking percent times the total to find each contribution, and then we should consider sig figs. Let's take a peek at this guy. Nitrox. It's a gas mixture used in scuba diving, and it contains a higher than normal level of oxygen and a lower than normal level of nitrogen. And they do that on purpose to help reduce the risk of the bends. Remember, I started our lesson when we first started our chapter talking about the bends. If you come up from scuba diving too quickly, your blood will actually start bubbling with nitrogen gas. Notice that the tank is reading 3,500 pounds per square inch. That's a number we had to read to find the percent of nitrogen and oxygen in this given tank. Well, let's count. Noticing that oxygen is going to be represented by the red. There are 3 oxygen molecules as compared to 1, 2, 3, 4, 5 nitrogen molecules. So looking at this contribution, the total number of molecules is 8. So the percent here, 3 molecules of oxygen out of an 8 total would give me its percentage in the tank. And then, of course, 35 psi, 350. The nitrogen would be the remaining percentage. So 3 over 8 is the percentage of nitrogen in the gas, right? So 3 over 8, this tells me, and then times 100. And then, of course, 5 over 8 expressed as a percent. You could simply take that value and subtract it from 100. You could say 5 divided by 8 and express that as 62.5% nitrogen. And that's just giving us how many how many total molecules we're contributing out of the total number. There's 3 red molecules out of 8 that represents the oxygen. There's 5 molecules out of 8 representing the nitrogen. So that breaks down to its percentage. And we can use that percentage then to find its contribution to the total pressure. And that's just what I had set up instinctively without solving for the percentage. 3,500 times 3 over 8 gives me the partial pressure of oxygen. And that comes out to me as 1312.5. And let's see, I'll just keep that as 1313, and that comes out as PSI. And the partial pressure of nitrogen then would be 5/8 times 3,500. And I'll round that as well to 2188 PSIs. In this recording, we are going to work a practice problem very similar to what we'll have set up in the lab this week. We're using a technique known as the Dumas bulb method for determining the molar mass of unknown volatile liquid. The word volatile simply means that it evaporates from liquid to gas readily at a reasonable temperature under 100 degrees Celsius. In this picture you can see that one method for the Dumas bulb method here is to take a hot plate, and in the hot plate you place some volatile liquid and you begin heating it, and over time all of this liquid would then turn to a gas and you could measure its volume. Ours would also look like this. So we're going to have a setup similar to a hot plate on this side, where we take a Erlenmeyer flask, not necessarily a bulb, but an actual Erlenmeyer flask, and we're going to create kind of a little cap on it with a piece of aluminum foil, and we'll put a little hole with the paper clip just so that the excess gas has a way of escaping. And you'll boil this in a hot water bath until all of that liquid has evaporated. You'll just visually be set when you don't see any liquid further down here. And then what's not shown but sitting over here is a cold water bath, and with a rubber gripper buddy or some sort of a clamp, you'll take this flask out once it's evaporated and you'll plunge it into cold water, and then what will happen is all of the gas will recondense to form a liquid, and that liquid then can be masked in terms of gathering data. So boil it and cool it to determine how much of the volatile liquid then recondenses to fill that entire volume of the flask. And let's suppose we just work a practice problem with the following data. So our job is to calculate molar mass of this unknown liquid by turning it into a gas and then recondensing it. The mass of the unknown vapor, so what we'll end up doing is weighing an empty flask and weighing it again at the end of the experiment to determine how much weight was gained by the condensation of the gas, 1.012 grams according to this data set. The volume of the bulb, in this set, the volume of this bulb here, or for us it would be the entire volume of the Erlenmeyer flask. Let's say that's 354 cubic centimeters, and I know a milliliter is the same as a cubic centimeter. And I also understand that when I ever do a Puvnert problem, the ideal gas law, we always have to be sure that we convert that into a liter unit. So I'm going to slide the decimals 3 spots to make sure that I remember. It goes in as 0.354 liters as the volume of our flask. The pressure that day, and again you'll just probably use your weather app on your phone to determine atmospheric pressure. Let's say it's 742 torr, which we understand is also the same thing as saying a millimeter of mercury. And therefore we know the R, the ideal gas constant, to match the torr unit is 62.4, and that is in millimeter mercury times liter over Kelvin mole would be its unit. The temperature looks like, as we're recording, is 90 degrees. Notice that your thermometer will actually be out here in the hot water bath, and that we'll assume the hot water is the same temperature as the gas inside. So if it's 90 degrees Celsius, we'll convert that to Kelvin, and we'll do so by adding the 273, and we get a temperature of 363 Kelvin units. We'd like to know the unknown molar mass. I know the ideal gas equation sets PV equal to nRT. Inside N is our target variable for molar mass. We know that N is equal to moles. And just remember that round little buddy trick where we have grams over molar mass is our mole. We're looking for this variable ultimately, the molar mass of our unknown. We'll do so by solving for n, the number of moles, and once we know moles, we can pull out molar mass. So just rearranging here, we know that P times V set over R times T isolates the n variable, the number of moles. Let's go ahead and work this problem just by subbing in those values. The first variable, pressure, was given to us as 742, and that's a millimeter mercury. Let me just give myself some room. mmHgs. And the volume we converted to a liter as 0.354 liters. Set over the product of the R constant, 62.4, and the Kelvin temperature of 363. Let's solve first for n, the number of moles. Hit with me to be sure I get a common answer with you. 742 times 0.354 divided by parenthesis, product of 62.4 times 363 Kelvin units, close parenthesis, and the number of moles I found was 0.1159. Let's just round that up to be 0.0116 moles. Now remember, molar mass is found by taking the number of grams and dividing by moles. From the story problem, 1.012 grams divided by that mole number we just calculated from solving our ideal gas equation. So let me hit that with you. 1.012 divided by that previous answer, and the molar mass I'm finding is 87.27, and my unit there is a gram per mole. We solve for n, the ideal gas equation. N stands for the number of moles. We then substitute, remember that round little buddy, I erased it, maybe I should put it back. Grams over molar mass is a mole. If this is our target, you can see our equation then says grams divided by mole pulls out molar mass, and that's exactly what we've done here. Let's try one more example problem together. Example 4, and that will finish your packet. The molar mass of a volatile substance was determined by the Dumas bulb method described above. The unknown vapor had a mass equal to 0.846 grams. The volume of the bulb was 354 cubic centimeters. Remember, that's the same thing as a milliliter, and when we use the ideal gas equation, we must put that in as a liter so that the R constant matches. The pressure of the system that day, again, just reading the barometer, 752 torr units. That also tells me the R, the ideal gas constant, will match that pressure unit as 62.4, and that's torr liters over Kelvin mole. And the temperature it's telling us is 100 degrees Celsius. When we use the ideal gas equation, we'll put that in as in Kelvin units, 373 Kelvin units. Let's find the molar mass of that unknown. I know that our target, when we set up our ideal gas equation, is n, the number of moles, because hidden in there, we know gram per mole is molar mass. So what we need to solve for first is n. The number of moles, just rearranging, is PV over RT. Here we had the pressure given to us as 752 torr. The volume in a liter unit, 0.354 liters. Set over our Kelvin temperature and our gas constant. We'll put 62.4 and 373 Kelvin. Remember, this is the product, so make sure we hit that inside a parenthesis. Let's solve for n, the number of moles. 752 times 0.354 divided by the product, so inside a parenthesis, 62.4 times 373, close parenthesis. I found N, the number of moles, to be 0.1144. And now to find our molar mass, we simply take the grams, which I forgot, 0.846, and we'll divide that by that previous answer. And let's see what we find. 0.846 divided by previous answer, and I get 73.97. About 74 grams per mole.
So PV over T equal PV over T. All three variables put into the same equation. I'll do a read through for number 1. Just a quick read through. Says we have 189 kPa, so there's our first pressure. So 189 is P1, 170 Celsius is T1, and it occupies a container with an initial volume of 15 liters. That's V1. We're going to change the volume, and of course the pressure will adjust. Increase to 7.5 atmospheres. Oh, I notice ATM on one side, kPa, so a little adjustment there, no worries. And the temperature is raised to 320. We're going to pull out for V2. Alrighty, so let me get my work set up here. So objective number 2, practice test C. So you're working on a round 2 opportunity. P1 V1 over T1 is PV over T for the second set of conditions. Question 1, I'm just going to assign the variables as we had read through them. First pressure was given as 189, and that was a kPa. First temperature I see was a 170, but of course we have to add 273 before we can plunk it in. And the initial volume given here was 15 liters. Let's go ahead and tabulate for the second set of conditions. By changing the volume, the pressure of the gas increased to 7.5 atms, and the temperature was raised to 320 Celsius. We're going to adjust for the new volume. So again, we're just quickly going to notice that there's a kP on one side, atmosphere on the other. So of course we understand that we need like units in order for the algebra to work. So here we have 7.5 atmospheres. We're just going to use the standard value of 101.3 kPa for every 1 atm. Remember that it absolutely doesn't matter if we change this guy into an atmosphere. We just need to use like units before we can put it into the algebra. 7.5 times 101.3, and that's 759.75 kilopascal. So quite a big pressure change. Let's plug this into our formula called the combined gas law. First pressure, 189 kilopascals. First volume, 15 liters. First temperature is 170 plus 273 is 443 Kelvin units. Pressure drastically went up, 759.75 kPas. Notice now we have like units. Looking for that new volume, and temperature 320 plus the 273 Kelvin is 593 Kelvin units. P1 V1 over T1 set equal to PV over T for set 2, pulling out for V2. So the algebra, cross multiply the side without the variable first. So key sequence, hit it with me. 189 times 15 times 593 divided by, and here's a quick thing, make sure we're using this big parenthesis, divided by parenthesis 759.75 times 443, close your parenthesis, equal 4.995 if you want to round. Let's see, put a liter in, so a liter comes out. Problem 1. Again, stop and process as you need to. Start the video again when ready. We have a 2-liter air sample at a temperature, it's quite cold, -50°C. Pressure is 1.75 atmospheres. We're going to solve for the new pressure. Temperature is raised to 50°C, volume expanded to 5 liters. Let's go and assign some variables. So problem 2, 2 liters, that first number, it looks like a volume number to me, V1 equal 2 liters. T1 is -50°C. We'll need to convert that to Kelvin before we use it. And P1 is 1 3/4, 1.75 atmospheres. What's the new pressure? So P2 is the target variable. Temperature is raised to 50°C, so T2 is 50, but I got to add 273 to get that to Kelvin. And that volume was expanded to 5 liters. Let's plunk them in. P1, 1.75 ATMs. V1, 2 liters. T1, well, 273 minus 150 is 123 Kelvin units. Is that equal to? Now look at P2 is our target. P2, since we put in an atmosphere, we'll get out an atmosphere, and that's going to be fine because it doesn't tell us otherwise. We get to select the unit. Might as well pick the unit that matches. The V2 is 5 liters, and the new Kelvin temperature is 50 plus 273, which is what, 323 Kelvin units. Hitting for P2, start on the side without the variable. So here's the key sequence. 1.75 times 2 times, oh, I have a calculator error, sorry, 1.75 times 2 times, here it is, 323, divided by, and remember, we have to put this parenthesis around this cross multiply, so parenthesis 5 times 123. 1.75 times 2 times 323 divided by parenthesis 123 times 5. That'll pull out P2 for us. And I had to insert my parenthesis. How about 1.84? Did I give you enough time to get there? I hope we match our answers. 1.84 ATMs. What's next? Given mass is occupying a 5-liter 745 mmHg and the temperature. So bam, first sentence gives us V1, here's P1, here's T1. Let's solve for the new temperature. Come back to us in a Celsius. If the gas is allowed to expand to 25, pressure dropped to 0.55 atmospheres. All right, no worries. I just noticed we have a mmHg and an atmosphere, so we'll fix that when we get our problem set up. Let me go ahead and record some of the information provided here. So here's problem number 3. Extend the page for us, give us room. First number I see is a volume, so there's 5 liters. First pressure number I'm seeing is 745 mmHgs. And the temperature is 25, but again I got to add 273 to convert to a Kelvin. Let's keep reading the next sentence. What is the new temperature? So here is the target variable, T2. We allow the volume to expand to 25 liters, and that pressure dropped to 0.55 atmospheres. All right, so just as we noted, mmHg on this side, atmospheres on this side. Probably easiest just to convert simply because I can multiply 0.55 by 760, and now we'll have 2 like units. That's what? That's 418. And now everything else with this guy will come out in a Kelvin. We can subtract out the 273. So remember, this must go in as a Kelvin. Even though it wants Celsius back, I always have to do the algebra in the Kelvin unit. Otherwise, it wouldn't get us the correct answer. Let's get our parentheses ready, as I always like to do. PV over T is equal to PV over T. Let's plunk in the numbers as we have them. First pressure, 745, include your unit, mmHg. First volume is 5 liters, and that's 298 Kelvin units. Pressure corrected to the same unit was 418 millimeter mercury. Volume expanded quite a bit, 25 liters. Let's pull out T2. Now this is a little different than the first two examples because now all of a sudden T2, which is our target variable, the side that contains the variable, here is that generally the way we always have started, but keep in mind we always cross multiply the side that does not have the variable first. So the first pattern is going to bring me this direction. So key sequence, hit it with me. 25 times 418 times 298 divided by parenthesis 745 times 5, close parenthesis. T2 is coming out as 836. Remember that that's Kelvin. Let's get rid of that 273 we had to add to get our final answer in a Celsius. And that ends up to be 563 Celsius degrees. What's next? Number 4, a gas was collected over water. Ding, 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 bells go off. This is an unusual problem. Collecting a gas over water means we have wet gas. So do you have this tool page ready? Question 4 and 5 will require this tool. It's called the water vapor pressure chart. Gotta have it. Soon as I read gas collected over water, whip out your water chart, my friends. We're going to need a little subtraction problem. Total pressure of the gas, 2.1 atmospheres. Temperature of the water given, 23 Celsius and 150 mLs. We want to adjust the volume to dry standard conditions. Dry, wet. So that's where the little subtraction comes in. I'm going to go back and just start recording some of these numbers so we have them handy. So here's problem 4. Gas collected over water, following data obtained. Total pressure of my system, total pressure, I'm going to give you just a little bit of Dalton's law review. Total pressure is coming from 2 individual gases. One of them is water vapor, and the other is this partial pressure of the gas we're trying to solve for. Total pressure is 2.1 atmospheres. Temperature of the water is 23 degrees Celsius, and the volume is 150 mLs. Now we want to know the new volume when we're at STP. So standard pressure, standard temperature, those 3 little letters really do give us numbers, don't they? Standard temperature, 273. Standard pressure is an atmosphere, is 1. Well, here's the scoop. This value cannot be used in the combined gas law just yet. It's the total pressure. This is the pressure we want to use for the PV over T. So this is where the little subtraction comes in. I've got to take the water pressure away from, or take it right out of, this total pressure of 2.1, and that's where the water chart comes in. And I remember, if I just remember looking at this water chart, there is no column for atmospheres, and it's just the way the chart worked out. We have mmHgs, we have a kPa, so let's take a peek. Our temperature was 23 Celsius, which puts me up here. Here we have 21.1 mmHgs or 2.81 kPa. What we have to do is convert either one of these into an atmosphere so we can subtract like numbers. So I'll just pick this one, 21.1 mmHgs, 21.1 mmHg, 21.1. And I want to just quickly convert that into an atmosphere so that I can subtract out like units. And yes, I hear some of you saying, couldn't I just convert this into an mmHg? Well, absolutely. It doesn't matter. We just have to subtract like units. So I'm going to choose to convert from my chart 21.1 divided by 760 gives me a value of 0.02776 atmospheres. And now that's the partial pressure of water. It's just in a like unit now to the total pressure that was given. P total of 2.1, subtract the value we just converted, so here's P total, minus the 02776 gives us the pressure of the dry gas. 2.5 minus my previous answer, and then I'm getting 2.472 atmospheres. I do a subtraction, now it's just a plug and chug into the combined gas law. The adjusted pressure for the dry gas, 2.472 atmospheres. The volume, 150 mLs. Temperature, 296, so I was adding 296 Kelvin. New pressure, standard value in a like unit. I have like units, we're set there. Standard temp, 273. Let's pull out the standard value for volume at standard conditions. So here we have cross multiply the side without the variable first, so key sequence 2.472. Let me clear my screen. 2.472 times 150 times 273 divided by parenthesis 1 times 296 and giving you a minute to hit it for a V2 is 341.99. Let's see, put a milli in, we get a milli out. Your answer will be extremely close, 342. No matter what you put in for your pressure unit, subtract the like units first. Make sure you put the correct standard value over here so that you have like units. Number 5 will be very similar. It's going to be of gas collected over water. Let's take a peek. Following data was obtained by gas collecting over water. Water chart, gas collected over water. We have an atmospheric pressure, mmHg, nice, no conversion necessary. Volume given, 1150 mLs, temperatures 35 Celsius. Solve for the dry standard conditions. Let me tabulate what we know. Total pressure given to us as 805 mmHgs. The volume is 1150 mLs. Temperature of the water, 35 Celsius. Solve for the new volume at standard conditions. Standard conditions in a like unit, 760 mmHg. Standard temperature in a Kelvin unit, 273 K. So here's the right side. I have a little bit of an adjustment yet here. I've got to take out the water pressure. So I got to subtract. Let's find on our water chart. The water chart says 35 Celsius. Here's 35. And the unit we're in is found on this chart. It's mmHg. So we'll have to subtract 42.2 torr units. 42.2 mmHgs. Subtracting like units will give us this dry gas. So let's hit 805 minus 42.2 and we get 762.8. This now becomes the P1. It's the pressure of the dry gas. PV over T. Plug them in. I like to get my parentheses ready. Plugging in the numbers where I know they go. P1, pressure we just adjusted to dry it up, 762.8. That's an mmHg. Notice I'm getting very good at remembering my units. 1150 mLs. T1 is converted into 308 Kelvin units. I want to know, let's see, 760 is the standard pressure. Looking for V2, there's T2. So let's see, we put a milli in, so our answer will come out in a milli as well. Let's hit it. Key sequence, start on the side without the variable. So here we have 762 0.8 times 1150 times 273 divided by parenthesis 760 times 308 close parenthesis equal. And we got 1023.07, so I'll say 0.1 mLs. And there's your A+ coming for your second objective.